Recordings rolling. It is Wednesday, May 14th. You guys have your quantum journals out, ready to go. We're going to finish these today. All right, so we'll do some half-life calculations. We talked about half-life a little bit yesterday. You guys remember this radiometric dating? Okay, so we're going to revisit that curve. And then, guys, by the end of class today, if you have this entire journal finished, because maybe you're here every day and you've got every quadrant, you can turn that to the gray tray, and I will put points in the book for that. If you've missed some of these quadrants, I know some of you guys been out for day testing here or there, then it's okay to turn in anytime in the next few days. So tomorrow, Monday, that'll be all right. We should have about 15 spare minutes at the end of class today, which would be a good time to, if you only missed like 3 or 4 of these quadrants, then you can, of course, pull up a video from last few days and then get the information that way. Okay. Laptops. So I think I showed you guys this yesterday. This is worth seeing again. Is now that we're winding down the year, be ready to clear all the information from your laptop and turn that back in. So seniors, they want laptops by this Friday. So you have about 2 days to turn that in. And everybody else, turn in your laptop by Wednesday, 5/28. So a couple weeks from now. You can turn your laptop into any teacher. I have a scanner right up here. So if you bring your laptop to me, then I will scan the barcode to get it back in the system. There will be a box that I can check that says that you also turn in your charger at the same time. So laptop plus charger. And then I'll file it away over in that roller cabinet over there. Right. If you are taking an AP exam in the next few days, because we've got a few AP exams left, remember to have logged into Blue Book within the last couple of days before you take the exam, so that Blue Book isn't trying to download a bunch of patch updates while everybody else is trying to get the exam going. Okay. Also, know your email and password information for College Board, because that will not necessarily auto fill in. Right, so you have to know that before you go into the exam. All right, so you guys got on laptops, exam information so far. All right. Okay. So one of the concepts you guys said I did. Now this was quadrant number 26, was this radiometric dating. Right, so we're looking at half-life, right? Half-life concept. Now this is a really generic curve. There's a bunch of variables. There's no hard numbers in terms of like exact number, how much time exactly has passed or how much amount you have, right? But that shape curve could apply to anything with exponential decay, or in this case has a half-life associated with it. Okay? So here's the basic concept: is if you start off with some amount of radioactive material. Now, a lot of atoms are stable, so this won't happen at all. But if you have something like U-235 or carbon-14, I'm going to use as an example, it'll have some associated half-life. So if you allow that amount of time to pass, one half-life worth of time, then you'll have half of what you started with, and then the other half would have decayed to the next part of the process. Like carbon-14, I know, wants to decay into nitrogen, and nitrogen would be stable from there on. Right? So if you start off with like 5,000 atoms, then after one half-life, you have like half of that, like 2,500 atoms. After another half-life, you have half of that, and then half that. So right, half of a half would be a quarter of what you started with. Half of a half would be 1/8 of what you started with. Right, so you guys see that process. Right? Now, what is the half-life for any radioactive atom? Well, it depends on the atom. So for carbon-14, you guys see it's going to be 5,000 some years. If this was uranium-235, I think it's like 700 million years, something like that. And a lot of radioactive atoms have a half-life that's a fraction of a second, maybe some milliseconds or something like that. So really a wide variety going on there. All right, so with that, I'll move on to the last few. Right, we're actually going to skip 28 nanotechnology. I have a space here for like what could be some engineering applications. Say if we like master physics, could you have like nanobots running around in your bloodstream, like clearing out cancer cells and that sort of thing? Yeah, probably one day, probably within our lifetimes, but we're just going to skip that one. So let's skip 28. All right, so you guys know we're skipping number 28. Don't worry about 28. Not going to score that one. Okay. Right. But we're going to do these last four. We'll do 29, 30. No, we're skipping 28. We're going right to 29, 30, 31, and 32. Okay. So we'll do these four here. Now, all these four are going to be related to half-life, but we'll look at different perspectives of this. Okay. So let's start with the intuitive type formula for half-life, which says that the amount that we have is equal to the amount that we started with. So A equals A naught times, right? And then in parentheses, do 1/2, and then take that 1/2 to the power of, So I'm representing that with a caret. Okay. We need the number of half-lives. Now, who remembers from yesterday, or maybe can figure it out? What fraction can be? It's going to be a fraction to represent a count of the number of half-lives that have passed in terms of the time that's passed. What fraction goes right there? Like for guys, for example, suppose the half-life is like 5,700 years, and maybe 11,000 years have passed. Okay, so if 11,000 years have passed, is that pretty close to 2 half-lives? Right. So wouldn't I have needed to multiply by half twice at that point? Okay. Right. Oh, so times a half, but how many times? So I need this ratio to come out to 2 if 11,000 years have passed. You guys get that? Right. So in terms of the variable t, what should I write? Yeah, t over t1/2. Right, you guys did. Let's see if you guys could correctly figure that out. Yeah, looks like you guys did. Right. So any time that's passed, like any number of years, compared to the half-life, which could be a known value for some radioactive substance, right, can give you a count of the number of half-lives that have passed. And that's a power on this 1/2. So you're multiplying by 1/2 that many times. You guys see how that fits together? Is that right? Now, give you guys a couple of specific values. Let's say, just for sake of argument, that the initial amount is 16 grams. And let's use a half-life, so T sub 1/2, so half-life of 5,730 years. Right. Okay, so now you guys know we're working with the carbon-14 because carbon-14 has that particular half-life. Right, so everybody knows we're working with carbon-14. Okay. Right, and let's make a table. So do 2 columns here. We're going to say how much time has passed in years. And what's the equivalent amount remaining in grams? Okay. So you guys got a 2-column table? Okay. Oh, so how many years have passed? Let's go 0, 5, 7, 3, 0. Let's go 11, 4, 60. Let's do 17,190. Okay. And just to mix it up and go crazy, let's try 25,000, which is, well, these first 4 numbers, you guys see there's a pattern going on. This one's going to break the pattern, but just throw it up, right? So, all right, so you guys good? All right, now I'm going to plug this expression into this calculator and plug in the known values for like half-life and the starting amount here. Okay, and the calculator should tell me how much radioactive material I have left out over after these times have passed. Okay? And the reason we're starting out with this, like this version formula and these particular years, which was like special intervals, like they're all multiples of half-life until we get to the last one. Okay, because I want you guys to see intuitively that this is going to work, so that when the calculator gives you the correct values, you say, I see that yes, this formula does give me something that I can believe like in my core is correct. Okay, you see like the premise of what we're doing. Okay, so let's plug this in. You guys got a calculator? So guys, follow along with me. So let's do 16 grams. That's in the A naught. Okay, everybody type this in. Okay, actually, let's do this way. I'll leave the last one to you. That 25,000, but we'll do these first 4 together. Okay. So 16 grams times, and then in parentheses do 1/2. You guys got that? You guys got 1/2 in parentheses. Okay, due to the power of. So hit the caret key. Okay. Any questions so far? How to get into that? Who's got that? Okay, so you got 1/2 to the power of, and then in parentheses, I need the time has passed as a variable over t1/2, which is the half-life, which is this time right here. So the first time is going to be 0 years have passed divided by 5,730. Okay. Hey guys, what is 0 divided by anything? 0. What is 1/2 to the power of 0? And don't say 0. 1. It would be 1, wouldn't it? Okay. And 1 times 16 must be. So when you hit enter on this calculator, if you did everything right, if you plugged in everything right, it has to say what? 16. Is everybody getting 16? Everybody should be getting 16, right? So, oh yeah, Because after 0 time has passed, you definitely have the amount that you're starting with, because there's been no time for any radioactive decay to happen yet. Right? Makes sense? Okay. Now, for these other values, all you have to do is scroll up, scroll over, and where that first time used to be 0, now I'm going to replace that with 5730 years. Okay. Now, after 1 half-life has passed, if everything's plugged in correctly, the answer must be what? Is it 8? It is 8. Look at that. It's 8. It's an 8 right there. Okay. How about scroll up, scroll over. Let's do 11,460 years. Great. Now, you guys see where these numbers are coming from? You guys see these are exact multiples of the half-life. We got 1 half-life, 2 half-lives. Later on, we'll do 3 half-lives. You guys see that? Okay. So 11,000 years should come out to, how much do I have left? Should it be 4? Hey, it is 4. It is 4. Look at that. You guys see this is all working? All right. Scroll up, scroll over. Let's do 17,000 years. 17 and change. So we get 2 grams, right? So it looks like every 5,000 and some years, it's getting half and half and half, right? Okay. Now, if I scroll up, scroll over, and I plug in 25,000 years. Ooh, right? I'll leave that one to you guys. Make sure that you guys have been following in the calculator. Right? If you're doing what I've been doing and all the numbers have been matching, right, which I want you guys to have been doing, right? Try it for 25,000 years. See what you get. I'm gonna write this off screen. See if you guys got this. All right, next one. So yesterday I told you guys actually 2 different formulas to describe this curve. Now, the first formula, you take the initial amount, multiply by 1/2 some number of times, right? And that's the formula, that's the expression we just used. Right? But it said if you actually like are a scientist working in this field, or if you're a mathematician, there's a more mathematically pure way to describe exponential growth and decay. And that's not with the base of 1/2. That's with the base of what? E. Right? And guys, what is E again? What is E? E equals 2.718 about, right? Of course, I have to round that because I have to cut it off somewhere because it's an irrational number, right? String of digits goes on forever, right? Actually, that looks more like this model right here on the poster, doesn't it? Right? Something like e to the power of. Okay? Now, what's special about e? Now, here's some notes from yesterday, but I want to remind you guys, also, some of you guys were testing yesterday anyway, right? Is what's special about e. So if I graph y equals e to the x, you guys see y equals e to the x, right? So, e to the 0 is 1, e to the 1 is e, which is 2.7. So point, there's a couple coordinates right there. E to the negative infinity approaches 0, like e to the negative 10,000 would be like 0.000 something, right? So asymptotically approaches 0 to the left. But going to the right, it takes off real fast, real big, because that's what exponential curves do. Right. Now, what if I have a stick figure walking up this terrain? You see he's walking from left to right. Okay, ground's pretty flat, flat. Like, ooh, okay, let's get a little slope to it. Right. Oh, okay, now I have more significant slope. Now I'm running to like almost a cliff, like all of a sudden. Ooh, right. So, what if I switch the question from not what is the y coordinate, because that's just this function right here, right? But instead, what is the slope of the ground underneath my stick figure? I see far to the left is pretty close to 0. And here, okay, it's on a shallow positive number. Here's a significant slope. And here's like a really steep slope all of a sudden. Woo. Okay. Now, if I hold my roller flush to the curve, if you guys see it, I can make a sort of a triangle shape. I can say, what's the rise over run? Now, I'm going to use calculus type notation here. I'll call this dy over dx, because I can make this infinitesimally small, so it just matches that point. Okay. dy over dx, rise over run. What's the slope of that point? You guys see the concept? Right. Now, here's a question that we covered yesterday, but I want to see if either you remember this from yesterday or can sort of figure this out, or maybe you already know this from a calculus class. Okay? If I come up with an equation for not y equals, not the coordinate, but dy over dx, say what's the slope of this curve at any point. Now, it does have to be dependent on x, because your x coordinate, different x coordinates have different slopes. So there will be x show up in this function. Yes, what's this expression right here that I'm covering up? It's what? e to the power of x. Yeah. Okay. Guys, is this the only curve in all of mathematics that does this? Yeah. So this has a special property where the y value coordinate and also the slope at that point, it's the same value. It's the same value. This is the only curve in all of math that does this. So that's pretty cool. Okay. There might be one reason why E is special. Right? You guys know if you have continuous compounding, say a bank account that's earning interest continuously, or maybe an index fund, you could model an equation. I think they call it PERT, right? P e to the RT, some version of that has an E in it. Okay. All right, so let's figure out the more mathematically pure way to represent the exact same information. So let's go A equals A naught times e to the negative kt. Okay. Now I'll give you guys that t1/2 is 5730 years, which means we're still talking about carbon-14. Actually, all four of these quadrants will be talking about carbon-14. Okay. But we got to solve for this k right here. You guys see this k? Now there's some value of k that's going to correspond to this specific half-life. If it was a different half-life, it would be a different k value, right? So we got to chase down k. I bet some of you guys can solve this. I don't know if everybody's up on their math skills, but notice what we're trying to solve for here is inside the exponent. Now, in this class of physics, I don't know if we've ever run it up to this. If we have, maybe once or twice ever. I don't know. Maybe not. Okay. But there's a special process. There's a special algebra process you have to use to solve for like how do you solve for something in the exponent? Like the last line is going to say k equals something, right? Also, I'm only giving you one known value. I'm giving you the half-life, and there's a way you can get it from that. But I see an A naught, a T, a K. That's a lot of stuff going on. Okay? So there's a little bit of creativity in setting out to solve for the solution. Like, what do you think the first step would have to be? Or how could you solve for K? Because there must be some hard number, like K equals some number. Okay, yeah, you could divide the A naught down, maybe, right? Now, here, how about this? What if I plug in this half-life for the time? Now, this is a variable time. You can plug in any time. What if you happen to plug in exactly the half-life into that time? If you did that, what do you know about the relationship between this A versus this A naught? Like, how about this? If you started with 16 grams, like you did over here, after one half-life, you should have how many grams? Yeah, 8. So 16 here would correspond to 8 here if you plugged in 5,700 years. What if you started with 10 grams and you plug in 5,700 years? Now you're down to what? 5. What if you plug in 22 grams and you plug in 5,700 years? Now you're down to what? 11. So the pattern is, if you plug in 5,700 years, what is A compared to A naught? Always. Yeah, it's always half, right? So I can do this. I can say, I'll get half of A naught if I start with A naught. And then I do e to the negative k, I don't know yet, but it is solvable. If I plug in 5,700 years right here, say years is the unit attached to that. You see that? Okay. So then, regardless of how much you actually start with, the A naught cancels out because you'll have half of whatever that is after 5,700 years. Is that true? All right, guys good? All right. All right. Now is the algebra step that we might not have applied in this class up until this very moment. Okay. To solve for something that's in the exponent, you have to apply a what kind of function? Logarithm. Aha. Yeah. Ooh, natural logarithm. I like that even better. Okay. Because if the base is e, that's what natural logarithm is for, isn't it? Right. So in general, a logarithm, and in this case, yeah, a natural logarithm is even better. In fact, you have keys for both of those. You guys see 2 keys in a calculator in the top left. One says log. Now, if it just says plain log, the base is what? Yeah, 10, base 10. And then right beneath it, it says ln for natural log. Okay. Oh, here, guys, here's a little forewarning too. I was taking a grad economics class, and the instructor was just writing log all over the place, log, 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 log. Right? And I was following the math. I was like, this doesn't make any sense. Everything's messed up. And it took me a couple of days to realize he was actually, I don't know why it's too long to figure this out. He was actually doing base E the whole time, but he was just writing in his log. So in case you have a college instructor that does that, but I'll just call it ln. So if I do ln as in the natural log of, as long as I apply it to both sides, won't the whole equation be balanced? Yeah. So natural log of the left side equals natural log of the right side. Oh. Ah. Yeah, right. Okay, yeah. So at least he's the next step. Right. So actually, if you skip straight to the next step, that's okay if you know what you're doing. Right. Because guys, natural log of e to the something. Now, one rule of logarithms is I can take the power and I can move it out in front and multiply it. So it's gonna be like the actually, let me do a second thing at the same time. Guys, natural log of a half, is that the same thing as natural log of 2 to the negative 1? Right. And then could I also take that negative 1 power and pull that in front? Is this right here the exact same thing as negative natural log of 2? Same thing? Right. I'll show you guys my calculator that works. Right. Let me finish this off. So negative 5730 k we're solving for, and then natural log of d. Let me show you that this is actually true. What's natural log of 0.5? It's negative 0.693, blah, blah, blah. What is negative natural log of 2? Negative 0.693. Oh, you guys see it's the exact same number? Right, so that worked out that way. Right? And it's really the same process we just did on the right side. We're just taking the power down. Right? Right. Now, guys, what is natural log of E? Natural log of E is 1. And in fact, you may have skipped that step. You might have just said, okay. Right? Like if you solved a bunch of these for math class, do you remember that process? You may have just like naturally skipped past all that. Anyway, okay. I'll show you guys that's also true. Natural log of e to the power of 1. That would be natural log of e, right? Natural log of e. Yeah, that's 1 right there. Natural log of e. That goes away. Right. Ooh, now we're getting really close. Guys, could I cancel the negatives if I wanted to? Why I pulled it out there. Right. Hey guys, what's the very last step to solve for k? Yeah, divide down to 5,000. So k. Well, if you want a perfect answer, it looks like this: natural log of 2 divided by 5730. Right. That might tell you, and 5730 is years. Right. In fact, you can kind of steal that format, and now you can get the k value for any radioactive substance. Isn't it always going to be natural log of 2 divided by the half-life? Do you guys see that? Of course, we derived where that came from. Right? If you want a decimal version, let's get a decimal version just for fun. Let's do natural log of 2, or actually, I might apply this later. Anyway, over 5730. That'd be 0.000120968. I'll round this a little bit. 121. That'd be 1 over years. Okay. Yeah, actually, I'm gonna use that decimal here going forward. Now this is rounded a little bit. Keep that in mind. So my answers might be off by a couple of years. Okay, because this is rounded a little bit. Okay, all right, guys, good. All right, third quadrant. Let's go back to do basically what we did before, except with the updated equation with the e in it. So we say a equals a naught times e to the power of, and then negative k, so that's negative, well, I'll call it negative kt, about that. Right. And then I'll give you guys a naught is, let's use the same 16 grams as before. And I'll give you guys k this time, which is 0.000121. That's 1 over years. Right. And that sort of takes the place of the half-life, because a half-life of 5,700 years corresponds to this k value. Okay. All right. Guys, catch up to where I am. All right. We got all that? Got all that. All right. Now, let's make a similar table to before. Let's say how much time has passed in years, and how much do we have left over in grams? Yeah, let's try some familiar looking numbers. 0 years, 5,700 years. Let's go 11,000 some years, 17,000 some years. Right. And let's have a wild card number. How about How about 19,000 years? Just make something up. Again, one of the reasons that I'm picking these really nice familiar looking numbers that are all multiples of a half-life, well, until we get to the last one, is because I want you to see that whatever numbers are showing up on your calculator screen, I want you to like feel deep down in your soul that, oh, yes, I see how this is all aligning, this all makes sense. Calculators tell me the truth, and it must be. So let's try this out. You guys ready to plug this in with me? And again, I'll leave the last one to you guys, so be plugging this as we go along so that you can get the last one. Let's do A naught, so we'll start with 16 grams. Multiply by, now I need e to the power of. Do you guys know how to access e to the power of? So on this calculator, you guys see that natural log key, ln? It's right above that in white. So I can access that with the second key. So hit second, and then e to the power of. So does everybody have that on their screen right now? 16 times e to the power of. Okay. And then I need negative kt. So hit the negative. Well, make sure you hit the negative, not the minus, but the negative down here. 0.000121 times, and however much time has passed. And the first time is just 0 years. So let's say times 0. Right, close parenthesis. Right. Now, intuitively, you guys know e to the power of 0. Guess what is e to the power of 0? 1. 1 times 16 is 16. It should say 16. Let's see if it does. Yeah, it is 16. Look at that. 16 grams, which is, of course, the amount we start with. So if we start with 16 grams and 0 time has passed, then we still have 16 grams. Right. Makes sense. Right. Now scroll up, scroll over, and where the 0 for 0 years used to be, I'm going to replace that with 5,730 years. Okay. You guys do the same thing? Okay. Now, before I hit enter, make sure you guys are following. What number ideally should show up on the calculator screen? Should it be 8? Okay, let's see. Ooh, 7.999. Yeah, so basically 8. Okay. All right, 7.999. But really, realistically, we don't even know 4 digits of precision. Yeah, maybe 2 or 3. So yeah, you can call it 8. That could be 8 right there. Okay. And I'm rounding this k value is rounded. Right, that's why it's not exactly 8. Okay. Scroll up, scroll over. Let's plug in the new time of 11,000 and some years. Ooh, 3.999. Good. Basically 4. Is that 4 years? Scroll up, scroll over. Plug in 17,000 and some years. 1.999. So basically 2 years. Okay. And this last one, I'm going to solve off screen and I'll leave it to you guys. So what about 19,000 years? So I'll solve it off screen. You guys solve it. Yeah, that looks about right. I'm sure about it. Okay. All right. Last quadrant. This is going to close out this whole journal. Is think about the actual application of this. Suppose you're an archaeologist one day. You're out in a place called the outside. You're digging with a shovel. Dig down a few feet. You find something that's organic material. Maybe it's an old bone. Maybe it's an old piece of cloth. Something that came from something organic. Something that was living at one point. Okay. You take that back to your lab. You run the analysis. Do you guys think whatever lab equipment is going to tell you sort of how many grams of carbon-14 you have? Okay. And what are you actually trying to solve for with this process? You're trying to solve for what? Huh? Well, how about this? We all have sort of the same initial concentration of carbon-14 in us. Right? Until you die. And after you die, that's going to follow this exponential decay curve, and it's going to tend towards 0. So if you were like 1,000,000 years old, right, you found like 1,000,000-year-old bones, at that point, it'd be pretty close to 0. Right? But all of us start with the same concentration. All living beings are going to start with similar concentration of carbon-14. Right? But so your machine analysis can tell you the concentration of carbon-14. You're trying to solve for what? Time. How much time has passed? How old is this artifact? How old is this bone that I found on the outside? Is it like really recent, like a couple of decades old? Is it like thousands of years old? notice that these three quadrants, we've been plugging in time values. Okay. But I want to change it up here at the end. I want to solve for how much time. So no, there's only a quadrant worth of paper there, obviously. So I'm going to go over and solve this on blank paper. So if you guys got some notes out, let's start with A equals A naught times e to the negative kt, right? But I want to rearrange this formula and solve for that t right there. So we're going to do that. Let's solve this in terms of variables. I know I've done this sometimes with you guys, but not super too often. My AP class, I do it more often, solve in terms of variables, but we're all going to do it right here, solve in terms of variables. Okay? So what's the first algebra step? Do what to both sides? Yeah, divide down this A naught. So A compared to A naught, the amount you have compared to what you started with, is equal to e to the negative kt. Right. Remember, here's our goal, is to solve for that t. Oh, what you're solving for is in an exponent. Oh, how do you solve for that? You have to apply a what? Aha, natural log. Aha, natural log. Okay, take natural log of the left side is equal to natural log of the right side. Right. In fact, if you've solved like 100 of these and you're really, really comfortable with it, you might skip one or two steps here. Because this is where like everything's going to fall in place. I'm going to take this exponent, I'm going to move it in front. So natural log of equals negative kt times natural log of v. Right. Or you may have skipped that step too, because guys, what's natural log of v equal to? Yeah, 1. It's just equal to 1, so that just goes away. Right. Right. Yeah, I'm gonna do one more little tricky step here. Guys, can natural log of this fraction be equal to negative natural log of the reciprocal? Is that the same thing? Right. I think we did one earlier today that was kind of like that. Okay. With like 2 or something. And the only reason I'm doing that is because if this side's negative, if I make that side also negative, can I do this? Just get rid of all the negatives. Right. Now that step is not 100% necessary, so you didn't have to do that. But right. Right. So the amount of time that will have passed is equal to natural log of the initial amount over the final amount, all divided by k, where k is a positive value. Right? Or if you had k as a negative value, then this natural log fraction would flip and be natural log of a over a naught, and then divided by a negative value of k. Okay. So there's a couple of different ways to write that, but here's one way. I mean, this should work. Right? Should that work right there? Right? It should tell you how much time has passed. Right? So you're the archaeologist. You dig up some old artifact. You want to know how old is this artifact? I mean, it's something organic. Right? So, right, we just did all this work. And let's take that expression right here. So the time that's passed is equal to natural log of the initial amount over the final amount, all divided by the positive value of k. Where, right, here's where I give you guys a couple of values. So the initial amount is, let's see, do you guys think that it more realistically be like some concentration, right? Right. So regardless of are you a mouse or an elephant, you probably have some similar concentration of carbon-14, right? So not in terms of grams, but how about like grams per cubic centimeter? Right. So I looked it up on the internet where everything is true, and I got this number, 2,000 femtograms per cubic centimeter. So we're going to use that. Okay. Also, since we're talking about carbon-14, this number would correspond to carbon-14. Okay. You guys know what K is because we solved it right up here. So I'll throw that number in too. 0.000121. That's 1 over years. Okay. Okay. So those are known values. Okay, so we got this rearranged expression to solve for how old is the artifact? How much time? Oh yeah, go ahead. 2,000. That's femtograms per cubic centimeter. Right, femtograms per cubic centimeter. Yeah. Yeah. Say we dig up a bunch of artifacts. you're gonna make a table right here. Make a table. So what is the concentration in femtogram per cubic centimeter? So we'll let the machine give us its analysis, its data, right? How concentrated. And then what does that tell us about how much time has passed in years, since that organism died? If it's some old piece of cloth, then right, when did they chop down the plant, start making the cloth out of it? Okay. So let's go with about 2,000, 1,500. I'll pick a wild card number. How about, let's see what I want to do here. Let's do, how about 160? Okay, we're just going to break the mold, but yeah. All right, so now these first three rows, these first three numbers, you should be able to work out intuitively. And then if you're getting correct numbers also on the calculator, that tells you that this whole process is actually working. Right. So let's try this out. So natural log. So everybody in their calculator hit natural log. You guys got ln for natural log? Right. So I need a naught over a. Now I know a naught is 2,000. So that'll be universally true. And then divide by, now a, well, but you get an artifact, and it also has the same concentration that it would for living beings. Couldn't you say that, oh, well, it's probably not been dead for very long, right? Maybe a decade at the most. And maybe it's an old chicken bone from like 5 years ago. Okay? So just hold on to that. Right? So 2,000 over 2,000, close parenthesis, divide by k, which is 0.000121. Right? So what I'm trying to get at is, when I plug in 2,000 into this expression, how much time should it tell me has passed? What number is going to show up on this calculator screen? 0. Yeah, that's 0 right there. 0 time has passed. Okay. Now, realistically, and maybe somewhere between like 0 and 10 years or something like that. So basically 0. Okay. Scroll up, scroll over. I'm going to replace the amount we found with, suppose it's half as much as it should be. So if something's alive, it should be a value of 2,000. We just found an artifact that has half of what anything living would be. That should tell me that how much time has passed. Who's going to get it? It has to be 5,700 years, 5,700 years, because that would be one half-life, wouldn't it? That would be one half-life. Okay. Now, truth be told, I don't know this level of precision. I don't know. It's 5728 exactly. They could say probably about 5,700 years. Maybe I know that much. Okay. Let's do 500 years. So scroll up, scroll over, plug in 500 years. Right? Guys, what does this number have to be? Aha. That'd be 11,000 years, because that would correspond to 2 half-lives. Right? Isn't 11,000 years like 2 half-lives worth of, right? Great. For carbon-14. Right? And this last one's a wild card. So I just made up a number randomly. I'll try it off screen. You guys try it. And let me see. Yeah. Okay. So the number I'm seeing on my screen definitely looks reasonable. Okay. So last detail with carbon-14 dating is this process really only works kind of for any organic matter that's up to 50,000 years old. Now, guys, once you go past about 50,000 years, this gets a little bit too fuzzy and it's not super reliable anymore. So it's kind of a rule of thumb. It's about 50,000 years. Right? Right. You guys good there? Right. So I'll leave that last row to you guys. Now, if you finish this entire journal, which you may have by now, then you can turn that to the gray tray. I will tick that off and give you guys points in the book. If you do not have this finished for whatever reason, maybe you were testing yesterday and missed a couple of quadrants, then I'll give you guys the last, we have 15 minutes of class left. You guys get the last 15 minutes to, you can open up your laptop. You guys know all the videos before today have been posted. You can find those, help each other out. You guys got some teammates. And yeah, you guys some time there. But that's a wrap on this class today.